My name is Hessam Babaee. I am an assistant professor in the Department of Mechanical Engineering and Material Science at the University of Pittsburgh. My area of research is at the overlap of scientific computing and machine learning. That is developing machine learning techniques to solve scientific and engineering problems. I was a mechanical engineer. I did my undergraduate, graduate studies in mechanical engineering. I also did masters in applied mathematics, but I didn't have any formal training in machine learning. At the time when I was postdoc, I was looking at uncertainty quantification problems. These are problems that have a large number of variables. I knew machine learning can handle these high-dimensional functions much more efficiently than the way we were doing it in the scientific computing. So that made me really excited. Tackle some of the unsolved problems in science and engineering. These problems, a lot of these problems haven't been solved because we haven't been able to actually do these computations. So if we have methodologies from machine learning that enable us to solve these problems, then there are a lot of new other discoveries that we can make. The mission of my lab is to develop reduced order modeling techniques and dimension reduction techniques to solve these high-dimensional problems. So we try to tackle two types of problems. One, problems that are, like I said, high-dimensional problems. You have so many variables. And there are another sets of applications that we are focusing on, and those are machine learning problems in extremely data-poor regimes. Our problems, these are engineering problems, data acquisition is very expensive. We're actually getting one data point requires an expensive simulation or an expensive experiment to do. So now with very few measurements, how can you train a machine learning model? My NIH project is, one of the objectives of this project is to reconstruct blood flow in a human brain by only having access to few measurements, which is what we have in a clinical setting. In clinical setting, we can find blood flow velocity only in few vessels. How can we take those few measurements and reconstruct the blood flow velocity and pressure everywhere in the brain? One of the projects I'm involved with is funded by NASA. And so this problem, we are looking at building predictive models for flow transition over aircraft wings. The input space is so high dimensional, it could be order of thousands to tens of thousands of variables. And obviously we cannot work with that high dimensional space. And so we try to reduce that number of variables to less than 10 number of variables. And that's a number that now we can start working with. So the way we approach these two ends of a spectrum, problems that are in extremely data poor regime or the problems that have way too many variables, is to reduce the dimension. Computing power has grown significantly over the past few decades. But the solution to these extremely challenging engineering problems cannot just come from just having a more powerful computers. You need to have methods, you need to have mathematical methods that can reduce the complexity of the problem. And so that's the overall goal of the mission of our lab.